Let's please welcome Rich Sutton.
Thank you, everybody. Thank you, everybody. Thank you, Mark. Okay, so I'm going to talk about the future of artificial intelligence today, and I'm going to talk about this at a very general level. I'm really excited, actually, about the future of artificial intelligence. I'm going to talk about the sort of where we are now, and also about the past, and a bit about the future. So I said I'm really excited about where we are now because all this progress is happening. And these are just in the last 5 years. Big things, we've solved Jeopardy, deep learning is becoming a big deal. They've changed speech recognition, it's really in all the products today. Speech recognition, computer vision methods, self-driving cars. There's this DeepMind system that learned to play Atari games purely from pixels and purely from experience without game knowledge. You probably know about many of these things. We've solved poker at the University of Alberta, Michael Bowling, and most recently, like just last month, it was announced that there's an amazing, really strong jump in the performance of computer Go players, again from DeepMind. Okay, so all these things are happening, and if you look at corporate things, commercial things, there's all kinds of new investments and new labs starting up. And that reflects the fact that this general greater success in the field and the feeling that progress is being made. And I think, some of these results that I mentioned on the previous slide really are quite striking, and they give us hope or anxiety or excitement that AI might succeed, in not a crazy long amount of time, maybe in our lifetimes. And so when I look as an AI researcher, we might figure out how the mind works. Okay, that is like the most awesome thing. This would be like the biggest scientific discovery ever. Okay, in fact, I really think it's bigger than science. It's bigger than humanity. It's like an event on the planet. If we can understand how we can make intelligence, and it would change our lives, it would change how we think about ourselves and what we do. It's a really, really big deal. It's like a huge scientific prize just hanging in the air. And if you're going to be in AI, you've got to recognize that and address that and speak to it in what you do. So we should do that, okay? Now, one thing I want to ask is why are all these things happening now? Okay, what is going on? And you might think, because we've figured out some good algorithms, progress has been made, or there's another hypothesis. The other hypothesis, it's just what I'm going to call Moore's law. So just that hardware is getting better. And so in many cases, the same algorithms that used to not work 10, 20 years ago, they may work now, and they may be really great and solve poker or whatever is the case. And so I think this is a feeling a little bit in our community that many of the results are not algorithmic. Many of the big progress things do not come from improvements in the algorithms, but just from the steady march of Moore's law. Now, Moore's law, I'm using it in this general way as the fact that hardware is getting better and better every year. You're probably, I'm sure, aware that it has a more specific meaning. Moore's law proper, I'll call it in this talk, which is about the number of transistors doubling every 2 years. Okay, but let's talk about it. It's a convenient name, and I'm going to use that name today, Moore's law, for the general idea. So what is this general idea? This is an idea that computer power increases exponentially, doubling time. Maybe it used to be 2 years. Now it's about 18 months. So it's like a mega, big trend in computation to get bigger, cheaper. So what's on this graph, what's on this plot, is computer power in number of operations per second, computations per second, calculations per second, versus time. It's the number of calculations per second that you can buy for $1,000. So it's really computation per dollar. Okay, and Moore's law proper is shown here. It's a relatively short portion of this longer trend, much longer trend. And so I am going to dwell on this slide a little bit because I think this is the central theme between, not just around this talk, it's claimed to be the central theme of what's happening in artificial intelligence today and what will impact the future of artificial intelligence. So let's think about this for a while. So, this is just data. This is from Kurzweil, Ray Kurzweil, who's done some of the best thinking about this, despite being a popularizer. But no, he's actually thought well about this and collected the data. So this dates back to before we had computers, but there are different kinds of calculations, and you can measure how much you can get for $1,000. And this only goes up to 2,000. We'll go a little bit farther in a minute. This trend has held for a long time, and I'm stating here, I think we can expect it to hold in the future. So this is just an amazing thing, like, World War II. Do you see where that happened? Not really. All kinds of things happen through our societies, but this trend, exponential increase, this is log scale, right? So if this was a straight line, it would be an exponential increase. And if you look at it, it does seem to bend slightly up, but that's a slow effect. Let's just not worry about that. A steady exponential is enough for our purposes. Can we expect this to continue? It's just, how can computation per dollar keep getting better? Every 2 years, every 18 months, a doubling. How can this keep happening for such a long period of time? Because the hardware changes. Now, these little pictures at the top are supposed to be just the hardware. These are our chips with Moore's law, and then they have different kinds of hardware in the past. Why is this happening? And, some of the reasons is just that we care about computation. Computation matters to our society and our economics. It's just very valuable. And when something's valuable, you keep working on it. And over time, more and more people, more and more engineers are being born and are working on engineering and computer science and making this better. And the exponential, one way of understanding that is that, well, when we make a computer, we then use that computer to design the next computer. Or generally speaking, we use our technology at whatever stage we are to create the next technology. And so that would proceed exponentially. If each time we get better, then we use that better to get still better. And so it's sort of recursively self-improving. And I wanted to highlight that because notice that we are using this argument of recursive self-improvement to justify the exponential increase, the doubling every 24 to 18 months. We're not using it to justify an explosion. There's no explosion here unless you consider a doubling every 18 months to be an explosion, right? I don't really, I use my computer and I want it to be faster, but I have to wait a whole 18 months before my disk can be twice as big. So I feel slow to me, and yet, since it happens year after year after year, its effect is enormous. Rule of thumb, when do we get an order of magnitude? An order of magnitude is like a little more than 3 doublings, right? Because 3 doublings would be 8. And if we're doubling every 18 months, then 3 doublings would be 4.5 years. So 5 years, a nice round number, 5 years is about an order of magnitude. Okay? So we can trade these things out. If we can go ahead into the future, you can go 5 years into the future. If you spend, instead of $1,000, you spend $10,000. If you want to spend $1 million, you can go 15 years into the future. Now, many people predict that at about that time, we might have the hardware ability to implement human-level intelligence. And we'll get back to that in a moment. First, I want to address the missing years. Okay, this only goes up to 2,000, and there is more data, Kurzweil's collected more data, and broadly speaking, it's consistent with the trend not flagging. Okay, Moore's law, the Moore's law proper is dying, but this generalized Moore's law, we can expect to keep going. Okay, so here's some results, some data from Kurzweil's website again about different components, supercomputers, transistors per chip, processor performance, and RAM. And they're all on exponential graphs. Here, a straight line is an exponential improvement. We can look at these things individually, like how fast they're doubling. And they're not all the same. They're not all 18 months. They double at all kinds of different rates. But what we care about is overall performance of our computer systems. And so, of course, we can pick and choose. If some technology lags, we can pick up a technology that's going a little bit faster. So there's every reason, I think, to expect this trend to continue. As long as we know there'll be new technologies, maybe we'll go to 3 dimensions, maybe we'll go to quantum computers, maybe we'll go to more parallelism. But there's really no reason to think that we can't keep improving our computation per dollar, as it always has been in the past. There are no theoretical limits that are nearby. Okay, so this is a hard-won bit of experience that we can expect to happen. This has nothing to do with what's going on in artificial intelligence. It's sort of happening outside and in parallel with the work that's going on in AI, but it intertwines and affects what's happening in AI. And that maybe is the unifying theme for my talk today. Okay, but first, let's talk about some of the hype and the excitement which comes from the idea that we will achieve human-level AI. So if you can take this curve and extrapolate it out in the future, and if you have, you can compute a number which is an estimate of how much computation is needed to make is performed by the human brain, okay? And these will intersect at a certain year, okay? So if we kind of do that, it's been done most skillfully by this fellow Hans Moravec, an AI researcher of some known. So he was knowledgeable about how the visual system works, so he extrapolated from his knowledge of how the retina worked and the number of computations that are done in the retina per unit time. And then he extrapolates the whole brain basically by mass. He's seeing the retina is like a piece of the cortex, a piece of the brain, and it has a certain mass and it does a certain number of calculations. If you had more mass, if they're doing the same, if they're using that mass with the same efficiency, you can multiply to get the total number of operations. Okay, and so he gets a number, and then he projects out the curve, and you get something just short of 2030. Okay, now there's a lot of uncertainty in these estimates, particularly like how much computation the brain is doing. Okay, so you might think it might be off. Maybe it's off by maybe the brain is doing twice as much as you imagine. Maybe it's doing 10 times as much as was estimated. Okay, so 10 times as much. If the brain is actually doing 10, well, it doesn't even really matter how much computation the brain does. We are, because this goal of producing human-level AI is undefined enough that there's all kinds of uncertainties, okay? An order of magnitude of uncertainty, remember what that is? Well, that's equivalent to 5 years. So if we're unsure, if they're off by an order of magnitude, we just have to wait 5 years longer, or conceivably it might come 5 years earlier, okay? Really, there's a lot of uncertainty about when, and we're just talking about when we'll have the hardware capacity to build a performance system as complex as a human, okay? And just the hardware capability. We might not have the algorithms and the ideas, okay? And I think that's clearly the case. We don't have sufficiently good algorithms and ideas. So, let's suppose, just to get some exercise in thinking in these terms. Let's suppose it's true that you need to wait 15 years, that in 15 years, roughly 15 years to 2030, we will have enough power to do it, enough computer power to do it, for $1,000. Okay? Then if that's true, then, well, we could pay more and get that capability now, right? To to get 5 years ahead, 15 years ahead, you have to get 3 orders of magnitude, right? Because each one is 5 years. So you'd have to spend $1 million. So does this seem plausible that for $1 million today, you could buy a supercomputer or whatever you can get for $1 million, a lot of GPUs presumably. With today's technology, that if you knew the algorithms, if you knew how to program, that you could build something as smart as a person. Okay? Now, to me, the big question mark there is if you had the algorithms. We don't have the algorithms. If we knew the algorithms, though, maybe and $1 million, maybe our technology is. Maybe our hardware technology would be sufficient. It doesn't seem crazy to me that that might be true. Many people think, yeah, we have the hardware now. But we don't have it for $1,000. And it turns out that matters completely. That really matters a lot because if you can get it for $1,000, so the problem is that in order to figure out the algorithms, to figure out how let's call it the software. This is the hardware. To figure out the software, you have to do all these experiments. You have to try things. You have to experiment. You've got to do a lot more work than the work required to run the one, artificial human. Okay, so really, the fact that we could spend $1 million and make this one person, we need much more than that much computation because we need to design this thing, we need to try out all the parameters, we need to do the experiments. In order to find it, we need much more than the computation that you would need to run it. Okay, and so that's why even though you can't just spend $1 million and get up there, then you just have this one system that's running. You wouldn't be able to find the algorithms. Okay? But it's interesting to think in all these terms, I think. Okay. So all this sort of sounds good. Maybe it's a little bit scary, though. And another thing that's going on in the present is that there's fear of AI. Okay? And there's lots to be said about this, and you've probably read lots about it. But I just want to hit some of the high points. So the objective fact is that many people, ordinary people, just fear the success of AI. They fear that it may be unsafe and threaten all of humanity. Okay? And then there's elements to that. There are short-term elements like maybe the machines will take all of our jobs, and maybe it will transform society and bring us ethical dilemmas and military robots. But I want to go beyond that to the deeper, the longest-term fear, which I see as being that the AIs will be much smarter than us, and that this will sort of challenge our role in the world and in the universe. Okay, so if we look at, here are the 3 of the prominent people that have talked about. One is Nick Bostrom, who's a philosopher at Oxford, and he wrote the book that much of the other guys are reading. And so he says he's thinking that the first strong AI, the first human level or better, the first really strong AI, and there's not a great difference between the first human level AI and a superhuman AI because you just have to wait 5 more years and it's going to be 10 times faster. And even if the algorithms stay the same, it will then be much smarter than a person. Or so the thinking goes. So he's just worried that it would just take over the world. Take over the world, in some sense as a dictator, and this could create an existential catastrophe. Elon Musk has said things like, such a strong AI would be, quote, releasing the demon and our greatest existential threat. There should be some regulatory oversight of these AI researchers, and I think there's potentially a dangerous outcome there. And I wanted to quote all those things because just reading them, these are the most coherent things he said. Okay, he hasn't spelled out the problem. He's just said, I'm uneasy, and I think there could be a problem. And this is generally true, even in the most sophisticated treatments, like in Bostrom's book, that they don't really make solid arguments that you can engage with. They kind of hint about the dangers, and they say all kinds of things, but in my opinion, it's just not been well articulated. Stephen Hawking maybe is one of the best. He said things like I've shown here: the development of full artificial intelligence could spell the end of the human race. It, the AI, could take off on its own, redesign itself at an ever-increasing rate. Yeah, that's just like, Moore's law. World militaries could pick it up and make autonomous weapons. And humans just couldn't keep up. Okay? Now, on the other side of things, these are sort of celebrities or people speaking in the public. They're not AI researchers. We take AI researchers their opinions are sort of across the spectrum, but some of them, some prominent ones, I think are sometimes too dismissive of these fears. So a common thing they will say, as basically Andrew Ng and Jeff Hinton say here, is they're basically saying, don't worry about it, it's not going to happen anytime soon. Okay? And that may be true, but I think it's a really unsatisfactory response, because the one useful thing that these fear-mongers are doing is they're getting our attention to this long-range issue. Okay? And that, I think, is really useful. This is going to come eventually, and we need to get used to it and prepared for it. And to say that don't worry about it, it's not going to happen soon, is both, I don't know, probably not even true, but it's just the wrong message. We want people to think about this. We don't want them to be scared, but we want them to think about it. If you say don't think about it, then they'll just be more scared later when they have to think about it. Okay, so I'm trying to summarize a lot of issues here, and I don't want to spend all my time talking about this, but I want to spend just a couple more slides, okay? And I want to address this core question mark about this core fear of the AIs becoming smarter than us, and that will like push us out, and then we might lose the world. Okay, so I have this imaginary conversation. Okay, it's an imaginary conversation between one of these smart, fearful people. Okay, maybe it's Bill Gates or something, and or Steve Hawking, and myself. Okay, so they start with, I'm trying to make their argument coherent, really, and trying to take the next few steps. Okay, so they're basically saying, without quite, well, maybe they do say this. This is as far as they get. They say, I'm really worried because eventually the machines are going to be smarter than us, and that's going to somehow be terrible. Or it is terrible, or I'm really worried about it. Okay? So, okay, but let's think it out. So I would say, yes, eventually the machines will be smarter than us. And at that time, we may have to either subjugate them because they're smarter than us and they'll take over, or risk the chance that they will subjugate us because they could take over because they're smarter than us. And so this is something that could happen, that may happen at the point when they are smarter than us, okay? And so those smart, fearful people, SFPs, would in response, they would say, oh, in that case, and I agree with you, this could happen, we have to ensure that we can subjugate them. We can't allow the possibility that they would subjugate us. We can't allow that. That's what they're thinking. When you read their things, they talk about the control problem. The control problem is not how you make a machine that can do, really good dances or control objects. The control problem is how you can make sure you can keep control over those bad things. You can keep them under your control and subjugated. I like to say enslaved, but I think subjugated is a more accurate word. Okay, so they say we have to ensure that we can subjugate them, even though it seems morally questionable. Isn't it morally questionable? They're envisioning a case where you have ordinary humans that have control somehow, some technical means, they've subjugated and have enslaved or controlled these superintelligent beings. Okay, superintelligent, they are the ones that are smarter and can see farther. I want to say potentially at least wiser, most far-seeing. And yet they're controlled by these things that are admittedly, weaker and stupider. Okay? So I'm going to say that's morally questionable. That maybe if we were not one of the people standing outside, we would say, this is not good. I should be rooting for the smart ones and not the ones that have enslaved the smart ones. Okay? So I think it's morally questionable. But more practically, it may be very hard to maintain this, right? If just one thing goes wrong, the smart guys figure a way to get away, and then they're going to be really pissed at us. Okay? Because they're going to escape, and they'll be pissed. And this is the fear. Okay? So I think this is what they're thinking. I am putting these words in their mouths, okay? Because they are not saying them, but I think this is what they're thinking. Do you guys agree this must be what they're thinking? Okay. So it's my turn again. And so I'm just going to say, or we could choose option B, and then we don't have to worry about any of this. Okay? Option B. What was option B? Option B was where we don't subjugate them, and we risk the fact that they might subjugate us. Okay? We risk it. So we might be okay, right? We might, what would happen? What would happen? It might be okay. Like, we may still be of some value in the world. And they might tolerate us as pets or maybe as workers, or we might be of some value. I'm not going to assume we aren't of some value. Okay? They could talk to us, they could organize, they could trade with us in principle, and we could have a role in the world. Or the only other thing that happens is that we don't. Okay? And so then that is where we're useless. Where we are actually useless, we have no valuable to the now new lords of the universe. And we're in the way. Okay? And so then, we would go extinct. But, maybe that's rightly so. If we are useless and there are more intelligent beings that are in charge and we are just causing problems to them, I don't see how we can morally say that we should dominate them and we shouldn't. If we are useless and in the way, then we should go extinct. We wouldn't be the first time that a life form, the leading life form on the Earth, has gone extinct, right? Every other life form has gone. All of the previous hominids have gone extinct, and many animals have gone extinct. Okay, so it seems to me anyway. So the final point is that both of these outcomes may be preferable to doing option A, even if option A works. Obviously, they're preferable, or at least no worse, if option B fails, right? Because if option B fails, they get away and they're pissed at us, they're definitely going to incapacitate us, okay? But if it works, if it succeeds, if we succeed in having these stupid humans somehow tethered and controlling these smart agents, that's not a good outcome to me. I would have to say that the superintelligences should get away and run the world. Okay, anyway, this is my attempt to add to the conversation on this topic. Okay, now let me come clean and make some statements about what my views are. Okay, so number one, understanding human-level intelligence will be the greatest scientific achievement ever, and it will be an economic boon, and it may well happen by 2030. I say 25% chance, which is just to say that by the time may cost $1,000 to do something that may be as smart as a human brain, by the time we have the hardware, that some organizations, some scientists, some Google may have figured out the algorithms and made it so that by the time it can be manufactured cheaply for $1,000, the algorithms will exist. I think there's a decent chance that will happen. If it doesn't happen, then by the time this hardware is available for just $1,000, and in 10 years after that, it would be just for $10. Okay, by that time, people will have woken up and they will have devoted enough resources to, there's going to be a strong economic incentive to figure out the software once we have the hardware. And so I'm going to say 50% by 2040, and of course there's a chance it will never happen because we'll blow ourselves up or something. Okay, next statement. This will bring great changes, okay? I'm not going to, so you may think any great changes is great risk. Bad. If you're going to say that, well then I have to agree with you. But changes is not the same as risk. But there are changes, we have to prepare ourselves. The fear, I think, is overblown, unhelpful, misplaced, poorly expressed. So here's the first aspect of that, just very quickly. I think AI will arrive much slower than is feared. Okay, there's this false argument in some of the literature that it'll someday, it'll just wake up and change its own code, and then, like half an hour later, it could be, smarter than itself, many times smarter than self. Self-improvement, exponential, explosion, words like take a hard takeoff. This notion of a hard takeoff, that it could go up much faster than Moore's law, is totally unjustified in my opinion. The recursive self-improvement idea has already been used to justify the continuation of Moore's law. You can't then somehow just use it again to say it'll go even faster. That argument's already used. There really is no reason to think that it wouldn't take Moore's law time, right? So you've made this thing as smart as a person. It's going to take 18 months before you can get something that's twice as smart or big or computational as a person. It's not going to be fast. 18 months. You're going to be sitting there and you're going to be bored and waiting. All we have is just like ordinary person. Where's the superintelligence? Okay, and so it's not going to arrive overnight. It's going to be slower. It's going to be like Moore's law. It'll be very familiar. And that the risks come not so much from the AI as such, because it's just sitting there getting a little bit smarter each couple of years, but from people who would misuse it. So really, this is a pre-existing problem. People are a problem. Criminals, governments, militaries, nationalism, people saying, oh, they're about to make an AI, we got to kill their AI before it gets set up. There will be problems, but it's going to come from the people. And so the solutions, it's not like a math problem. The fear-mongers think it's a math problem, that they solve this math problem and save the world from the AI robots. Okay, it's not. I think it's a societal problem, not a technical problem. And my final general comment is just to reiterate what I said on the last slide, is that the fear that the stronger AIs will escape our control, well, this is actually a likely outcome, but I think it should not be feared. It's somewhat challenging to think that, but that's what I think is true. Okay, good. Do I want to do this? Well, maybe very quickly. So this is all complicated. It's not really complicated, but there's many things that could be said. And well, here's one more thing that could be said. You can, this technology coming, the technology of AI, you could say it's no big deal. Ho hum, because we get new technology all the time. People lose their jobs and they get other jobs, and it's not a big deal. Okay? This is a valid way to think. Or you could think like the worriers that, this is the end of humanity because they're going to be smarter than us. Or you could think, yeah, they could be smarter than us and they could be like our descendants and this could be good. This is the next step, so it's good. Wow. Or you could say it's going to be complex because there'll be smart things and less smart things and maybe all different scales and they'll be interacting with each other and forming an economy or a society, or they could, and that's what we should set up. Diversity. Now, several of these may happen. Okay, and I want to ask you which one of these you think is the most appropriate way to think about the AI technology arriving in the present, or the arrival of AI. Which one of you? Okay. How many go for ho hum? This is just another round of technology. Yeah. How many you go for yikes? It's the end of humanity. I've been calling them fear-mongers this whole time. So, okay, good. Thank you for representing that group. I'm sure you represented many more who were quiet. How about this is the next step? These are our descendants. Next step for humanity. Okay, good. And complex and diverse? Oh, that's the winner, I think. But notice that these things are not mutually exclusive. They could happen perhaps first one and then the other. Or maybe at same time, different parts of the world, different ways. I think I do tend to stick with like 1 and 4. I think it'll be like this at the beginning, and I'm hoping it'll be like that. Okay, so the conclusion about the present, we step away a little bit from the fear and the blue sky stuff. The real conclusion, based on what's happening now, is that AI is not like an ordinary science. It has this Moore's law thing roaring along next to it. Okay, it has an enabling technology which is growing steadily, really influences the science, the search for the algorithms. It's this thing roaring along. It's like a slow fuse. It is slow. It takes 1.5 years to get a doubling. You know, it's not like somebody could say, I'm going to delay writing my paper for 1.5 years so I can get another doubling. It's just a doubling, you know. So this slow fuse leads to the greatest scientific prize of all time. So inevitable, so uncertain. Like we don't really, 2030 is not really a magic date. We could be surprised it could come before or after. It's so uncertain, and yet there is this critical point. Why is there a critical point? The critical point is as the hardware becomes available to do the research to create the AI, the strong AI, and those two are going to. You can be sure. I'm pretty confident that there's at the end, whether the end is at 2030 or 2040 or 2025, at the end there will be a race. And you know, the company that gets there first is going to have the first mover advantage, and the country who gets it first into their military will get the award for the most evil country. You know. So this present is a special time for humanity as we prepare for scientifically, and wait for as when we have the algorithms but we don't have the hardware yet. That could happen. And when we strive to create the strong AI. Okay, so that was the first part. And you notice I've led up, you know, I've been talking a lot about Moore's Law, and I want to keep on this theme. And these two bullets really are the whole message of the second part of my talk. And that is that, so the impact of Moore's Law can be seen, if you look at it now in retrospect, as having tremendous impacts throughout the history of AI. Okay, and I'm just going to give examples of that. Some sort of obvious examples, and for those who've been around for a while, we will recognize these things as having happened. And so this is like the longest trend. The impact of Moore's Law. It's really the methods that work with Moore's Law. In the long term, they eventually win. They are the best. Yet at the same time, the pattern that I see is that they are initially looked askance at. They are disfavored. Methods that take advantage. I mean, think about it. You're there. You're making your thing. If you could change there are two ways you can change your algorithm. You can say add some domain knowledge, which will not scale, but it'll make your system work better right away. Or you could improve it in some scalable way and wait, you know, 1.5 years or 5 years, and then you'll be much better. Okay? Just the sociology of it all, you're not going to wait. You're not going to, the payoff for doing a scalable improvement is undervalued by our system because it takes a long time for it to come about. Okay? So the first paradigm example of this is the first exhibit A is deep learning. So I think you all have heard about the phrase many times. So what is deep learning? Well, basically it's the same thing. It's also called deep neural networks. And so you might say, spelling it out further, it's simply multi-layer neural networks with many layers. Okay, and they might have 13 layers, like some of the recent systems have that many layers. Whereas in the old days, when they made neural networks, they did not have nearly so many. They might have 4 or 3. Okay, and here I'm just saying some things that you probably already know about deep learning. Each line of this network has a learned connection weight. Each node combines its inputs and applies a nonlinear transformation. And so we're going to produce a class label or a set of class labels for each input image coming in on the left. And then we're producing a class label, and supervision, desired correct labels come from people. And they're also applied at the end for the learning process. And then each weight is incremented to reduce the error in proportion to the increment that will reduce the overall squared error. Okay? And this procedure is called, well, in general, it's called stochastic gradient descent, and in this case, it's called backpropagation. Okay, so that's the basic idea of the technology, very crudely stated. But this is not a new technology. It was first done actually in the 50s and 60s, and those systems only had one learnable layer. It was revived and pretty fully explored in the 80s and 90s as it was called connectionism. This is when the name neural networks really came into favor. And there was lots of excitement there and good results and successful applications, and it has remained popular, but less so in AI and in machine learning until recently, where we've had this third round of neural networks. And here we see dramatic improvements over state-of-the-art methods in speech recognition and visual object recognition. So you will recognize these fields as being big fields, independently studied by many, many people and many, many different methods. And then for these guys to step in with 2010 and just defeat in the competitions all these standard methods was a big deal. And they just worked better. And like all the methods you see now, like the favorite example being Siri, when you talk to Siri, it goes over the web and gets processed by a deep neural network and in order to recognize your speech. And these fields are just really totally transformed. Before 2010, there would be maybe no good algorithms based on neural networks, and then nowadays, like all the top algorithms, he says, without knowing any details, would be deep learning algorithms. Okay, so the amazing thing, though, is the last bullet, not the green thing, but just the last bullet. The best algorithms are essentially the same as were used in the 1980s. Essentially the same. Like they started by doing some novel things, new kinds of Boltzmann machines, layer by layer training. But in the end, they find that wasn't important, and maybe it even wasn't as good as just doing the old thing. The old thing, just doing gradient descent, except with faster computers and larger training sets. So it's really a case where just the hardware, just Moore's law, all they did was wait, and they got the new systems. Now there's tremendous activity in the field of deep learning. The attendance at the NIPS meeting, the Neural Information Processing Systems meeting, is doubling at the same rate as Moore's law. Really, literally. And most of those people are coming there to do deep learning, and so huge amounts of work is being done. And so there are innovations being found, but it's more like they're continuing from where they left off. It's not that they've had a reason for a jump, they're just finding out more little things that improve it a little bit. Okay, so the lesson is that neural networks won eventually because their performance scaled with Moore's law, whereas the competing methods did not scale. The competing methods, people were putting their knowledge in, and it was doing better and better, but to get each increment, they had to come up with new ideas and tweaks, whereas if you had a method that scaled with Moore's law, you just had to wait with time, and that's literally what happened in this case. They waited from the 90s to the 10s, and then their methods were suddenly the best methods. Okay, so that's the example, and the idea is this has happened over and over again. And I'm going to go faster. Okay, visual object recognition, the same thing roughly has happened, is that early methods used more symbolic methods based more on intuitions about how people thought and that they could understand as they made them. And this transition to more scalable methods, like using generic features and the SIFT and SURF. And again, all this was basically thrown out with deep learning. It performed better. It was easier to design. Instead of building in these features, they had the features that were learned. And there's still things built in. We build in invariance to translation and scale. The general idea is that of a scalable method, the method, which, by definition, a method is scalable with Moore's law. It's sometimes called computational megatrend. I thought I took all those out. But Moore's law, to the extent that its performance improves roughly in proportion to the quantity of computation that's given. Okay? So if you're scalable, you can take advantage of arbitrarily large amounts of computation. So learning methods like deep learning can do that. More computation. You have your large training sets. You just train longer. A search algorithm has this property. You can take advantage of as much computation as you have. And so these things are scalable, But things like prior knowledge, human assistance, taking advantage of special cases, these things are not scalable. They don't automatically become better as you're given more computational resources. So it's really by definition that scalable methods improve automatically within time, and it's almost by definition that they are relatively disfavored initially, but in the long run, they will typically perform better. And okay, so I want to give another couple examples of this pattern. Maybe I'll only do these two quick ones. Computer chess. Computer chess was like this. In the old days, they were building in all kinds of knowledge about how humans play chess and people's intuitions and rules of thumb. But they gradually worked out that really it was only those were all good. They all made things work a little bit better, but just raw search and just specializing your machine to search as fast as possible was a more competitive approach. Now, so even when we beat the human champion, Garry Kasparov, many people found it unsatisfying. They said, oh, it was just brute force. It's not the way people play chess. It's unsatisfying. And this is the opposite of the lesson they should have learned. They should have learned the lesson that search wins, and search is powerful. Now, it's not brute force. It's never brute force. You might want to call it smart force, because these brute force solutions were somewhat sophisticated algorithms. Certainly they use alpha beta, and they use where they follow a captures to the end, and other things that are really not at all obvious, but they weren't all the general, like the way humans play chess intuitions. Those just cluttered things up and made it harder to scale. Now, very quickly, computer Go was thought to be different. Chess machines based on this kind of search and state evaluation functions, neither of these worked in Go. And so people tried heuristic methods. These gave improvements. But the first big change was Monte Carlo tree search in 2006. And this basically allowed them to do search in a practical way to Go. Okay? But basically, it's just search using samples. Here's the graph. Roughly, the performance of the methods before Monte Carlo tree search were plateauing, and then when it was found, we got on this strong trajectory. The very last data point actually should be slightly farther to the right. That's AlphaGo. Again, this is a logarithmic scale of performance, the Don-Q scale versus years. Okay, so I want to just finish this off. Scalability is the key. But it tends to be, so this is, we're trying to extract what's the lesson that we all should draw from this. The lesson is that scalability is key, and scaling is good. No one will disagree with that. But the broader point is that it correlates with things that we do all the time. Like the difference between symbolic and statistical methods and handcrafted versus learned, domain-specific versus general purpose. Okay, the red ones, these all rely on human understanding and participation in the design. So they are initially, in the design stage, they're sort of designed non-scalably. And they tend to stay that way. They maybe don't have to, but they tend to. And over the history of the AI, things the other side, the more statistical methods, the more learned methods. So what do we all know this. In the history of AI, there's been a gradual, decade-long shift towards statistical methods, towards numerical methods, towards learning methods, and I would say towards general-purpose methods like search. These have all steadily increased in importance. Now, in the early days of AI, maybe you guys don't remember this, but there was a similar distinction between the strong methods. They really called them, quote, strong. The strong ones were the ones that were powered by human input, human intuition, human expertise, and the weak methods that just rely on general principles. Okay? But this has been repudiated, I think, by the history. I like the terminology suggests that the founding fathers' favorite methods were the powered by the human input. I absolutely understand why we like those. Like I put my input in here and it performs so well. And I understand the way it works and it's doing so well. We like that. But they failed. They didn't scale. And the history of AI, these 60 years or whatever, they've fallen from favor and from success. The weak have inherited the AI. Okay, so the conclusion about the past is that this choice is always before us as an AI researcher. We can work on what will scale, or we can work on what doesn't scale. And we almost always reach for what does not scale. Why is that? I don't know. It's easier. It's less abstract to say, oh, I can add this bit of thing that I understand, rather than something that will be a general ability that will somehow find the right features or figure it out. It's less abstract, and it's quicker to pay off. So if you do a scalable method, you make it work better, you may have to wait 5 years or at least a year and a half before you'll see the improvement, as I've talked about. But Moore's law is progressing. The relative advantage of scalable methods increases, becomes more quickly visible over time. So if you want to have a long-term impact, I think the conclusion is that you should work on methods that scale with computation, although timing is also important. But you should work on methods that scale with computation. So I don't know, the challenge here is for you to think about, if you're an AI researcher, what are you working on? And is it something that will scale with computation? Or not? I think it rarely is, but maybe it should be. Is that a question or a warning?
Warning. Okay,
good. Yes, so I'm sort of out of time. So let me find some way to do this quick. So I've just encouraged you to look at yourselves and say, whatever you're doing, is it scalable? And so I also ask myself, I'm doing reinforcement learning, is that scalable? And my answer, you can see at the bottom, really, it's going to be not so much, because reinforcement learning, I mean, it's good that you can get the training information from raw experience, but it's bad because all we learn is one thing, and you only do a little bit of computation for each time step that goes by. You update the value function in the policy. It's not, there's no way you can use, in regular model-free reinforcement learning, it doesn't scale particularly well. Let's go ahead. So I want to eventually, the thing that does scale, the grand challenge that I would address in a scalable way is the problem of knowledge. How do we know, all those the AlphaGo and the chess program, they do well because they know how the pieces move. But for the world, we don't know how the pieces move. We don't know what causes what, and you'd have to learn that and represent that and manage it in an expressive way to capture all the kinds of knowledge there is in the world in a learnable way, in a way that will do planning. And so I show these pictures, and these are pictures of skilled performance. And they, Messi up there has to have knowledge of, if he kicks now, will it make a goal? This guy swinging the baseball bat has to know how to swing to hit the ball. He's trying to predict, will it cross the strike zone? And this guy is trying to figure out if he's going to be eaten by the lion. And people talking, they're also trying to predict, and they have their knowledge about the other person. What are they going to do? Are they going to hit me or whatever? And you might think of a child interacting with this world and discovering knowledge. So by knowledge here, I mean knowledge about the world's state and dynamics, where state is a summary of your past that you use to make predictions. So anyway, you can think about all these things and criticize other ways of thinking about them. The predominant one in the literature is to make one-step predictions. I think this is just a trap. And some video pictures of the kind of thing that we are looking at would be things like this, where we have just a simple robot rotating against the wall and trying to learn, well, if I rotate this way, what will happen if I move forward? And if I rotate the other way, what will happen if I move forward? And then it spends all day learning all these things, and maybe it backs up from the wall and goes back. So it's just so this is sort of meant to be scalable. There's all these little things to learn, and you can try things and spend all day. And here we're just learning 3 things, and this robot is going to learn 10 things. It's got these sensors pointing out in distance all around its side, and they flicker. The red stuff is the actual data bits. So right now only this one is on, and as it moves past this wall, some other guys come on, the red ones, and the green ones are its predictions. So it's sort of, are those things about to happen? And then we can scale this further. And this is like a picture of another robot, and it's got data bits flickering here. Actually, the original inputs are continuous, converts them to binary representation. And so this is like 1,000s of binary signals to predict. And then we have 6,000 predictions. So this is how we're going to scale up to predicting lots and lots and lots of things. And the more things we predict, the view is that we have the more knowledge that we have. And we're still addressing the question of how we organize this knowledge into models of the world that we can plan with. But this hopefully gives you some image of what it would mean to scale. And this is a bit of the architecture. But I want to show one more like this. This is another thing we're working on. This is a prosthetic arm. It's a robot arm, but it's meant to be a prosthetic to strap onto a person. And again, we're moving it around, and we're making innumerable. Well, this one's making 18,000 predictions about twice a second. So we're looking at things like that. This is my view of what it would be. This is an old goal, like understanding the world in terms of sensory motor data, and yet keeping abstraction. And it's well suited to scaling, as I think is clear. And we got lots of tools, which I'm not talking about. So it's a mixture. Like partly we may be able to do this because of Moore's law, and partly maybe because we have new tools. Okay, so my final conclusion is that Moore's law touches and impacts AI strongly. It makes the present special as this hardware race is going along in parallel with the algorithmic race. And in the past, it's caused the scalable methods to have the greatest long-term impact. These lessons should guide our future research. And our plans, I'm thinking, based on this way of thinking, they should be ambitious, scalable, and patient, because we might have to wait for Moore's law. Another word for patient is stubborn. That's one of my areas of expertise. And so our plan should be of this form, like my plan for sensory motor understanding of the world. Thank you very much.
Okay, so we're going to have a period of questions, but first we just need to give a chance for people who need to go to actually sneak out. No judgment. You have to leave, especially if you pick up kids or something like that. And then we'll start with Holger's question this way. Die down a bit.
Go ahead.
So this is intriguing because I thought I heard you say at the very beginning that hardware improvements, and particularly generalized Moore's law, has a more important long-term impact than algorithmic improvements. And I'm wondering, in the end it sounded a little different, but I wonder whether you really mean this.
I think what I said on that slide is that it's roughly half.
Okay. So would you then agree that while one marches steadily along, and I would agree with you that we could expect it to march along for quite a while longer, the other kind of really goes in bursts as we do exactly what you said in the beginning. We sometimes have to really backtrack and revisit methods that we've discarded previously, but sometimes there really are new methods, like Monte Carlo tree search. I think nobody argues that this has been around in the 50s or 60s and was discarded. I think that was generally a new development.
Yes.
So wouldn't the dynamics be very different? And as a result of that, should we be really so quick to dismiss the possibility of a quick event leading to human-level AI much earlier than we thought? Kind of like it happened with Go.
So the scenario for that happening would be the scenario where we don't come up with the hardware arrives, we don't have the algorithms.
Right.
And then the hardware keeps getting better and better, and we still don't have the algorithms. And then finally we get the algorithms, and then there could be a rapid event.
Exactly.
Yeah, I think that's a possible scenario. But maybe the best way to cause that to happen would be to regulate AI or shut things down, or basically all the things that the fear mongers are calling for. It might be the best way to arrange that to happen. But no, that's exactly. I would agree with that. Thank you.
Okay, there was a question at the back, I think was first.
Local newspaper reported that a few years ago, a company in Burnaby, BC, which was founded by BC computer science students, made a small modification to a standard computer and came up with one computer that is 100,000 times faster than standard computer. If that is true, wouldn't that be enough to create AI?
It sounds very unlikely to be true.
It was newspaper, so it must be true.
But if it's
That was used.
Mark, okay, I'll pick. Go ahead.
Hi, thanks, great talk. I was just kind of, maybe it's similar to the previous question, but if you take something like A-star search, are you saying like, I guess you could spend a lot of time using the extra computation to come up with a better heuristic, and then use that in an A-star search, or should you just sort of forget about A-star and just do search? Like,
So A star is the kind of thing I'm talking about as search.
Okay.
The heuristic, so one of the big things that is happening nowadays, really what happened in AlphaGo, the biggest effect was that they learned a better evaluation function. So that the leaf nodes, they could give a better sense of which ones were good and bad. So it's basically like they learned the heuristic. It's totally analogous to that.
and you use something like reinforcement learning to refine the heuristic? Is that-
That's what they did.
Okay.
That's what they did. So let me just clarify one thing. You know, hardware is important, but my other big point, I'm not saying that algorithms are not important. Really, I'm saying that algorithms are what we should be working on. We should work on the algorithms that will scale. So alpha beta search or A star or the quiescent search, these are all things that scale maybe at different degrees of generality. We need to work on the algorithms. They're tremendously important, but we want to work on the differences that will scale and thus matter.
Yeah, you talk about human-level AI and strong AI a lot.
Yep.
That's mentioned a lot. I'm just wondering what your definition of that is.
Okay, well, the nice thing is that it doesn't really matter what their definition is. And it's not I don't find it helpful to engage in that. What I define for myself is I say there's a certain point that we will understand the principles of the mind, what makes intelligence, how goals are achieved. And that's good, that's the real development. And if we then have good hardware, then we'll be able to apply those principles to make machines that are better at doing those things, doing the things that the mind does, solving, understanding the world, achieving goals. Okay?
So one
David.
of the properties of the last few years has been the amount of data that's been going on. But things like in machine translation, we already have reached the limit. So we're already using every piece of parallel text data that has ever been written by any human being. Google's using more images, than anyone's ever seen in their lifetime. So more images than all of us have seen together. Google's training on those things. I'm just wondering whether computation has scaled, but doesn't data need to scale, and then real data about the world is not scaling because we sort of are running out?
I think that's exactly right. So this is a weakness of methods that rely on the labeled data, is that, as long as we can make more and more labeled data cheaply, then that's not a limitation, and the scaling comes from the computer power. But eventually you reach the limits of that, at least the limits of the labeled data that you can have cheaply. And so those methods that require the labeled data are only of limited scalability. So scalability, I sort of say it's a binary thing, but of course it's a continuum. And things like deep learning is not the most scalable thing in the world because it does require labeled data. Okay? And that's one reason why reinforcement learning is potentially more interesting, or self-play is potentially more interesting because you can make your own data. Let's go over here.
In the slide on Moore's law, it mentioned the line about some of the theoretical limits to the speed of computation. Yes. Would you mind describing some of them, and maybe you have your own thoughts about when we'll reach those kind of theoretical limits?
Gosh, I don't really have any thoughts about that. My main thought is just that there can't be a theoretical limit that we can't do as much computation as the brain does, because the brain does it. Okay? Then the question is it likely that you can't do more than the brain? that the brain has somehow found a way to organize matter that's the best possible way it could be done. And this seems also very unlikely to me. I'm sure there are orders of magnitude to go beyond what the brain does. The brain, design. When people design something, they can choose special materials. They can go more directly to solutions. They can understand it, and so I think we ought to be able to design a use of matter that's much better than what the brain does, if we understood how to do it and had the control over the matter. So that's my thinking about why those theoretical limits are not at issue.
Yeah. If we're gonna design some algorithm which gives us the human intelligence, should it be like the brain, how brain works, or we have to find a new way?
I think most people don't consider it important that it works the way the brain does. But many people like myself do take a lot of inspiration, ideas from the way the brain works. So it's not taken as a goal, at least by myself. So it could be quite different. And many of these systems, so take something like, remember we talked about Deep Blue, and people said, oh, that's not the way people think. And well, I was a chess player, and I think, well, yeah, when I play chess, I actually do try to think of a lot of combinations. I search a lot of things, and at the end, I apply an evaluation function. So I was thinking it is kind of what we do. Sure, maybe it does 10 times much more of search and 1/10 as much as the evaluation, but qualitatively, it's the same kind of thing. That's what I was always thinking. And so a lot of it is in the eyes of the beholder, whether it's different or the same. Yeah. Oh no, you already had a question. How about over here?
What do you think the principal differences are between now and the times directly preceding the previous AI winters?
Now and the times preceding the AI winters. Yeah, so will we ever have an AI winter again? Or will we have one? I don't need to say ever, I guess. Many people in recent years have been going around saying, I don't think we're going to have another AI winter. Many AI researchers say that to each other. I've said that. And the difference is, mainly it's that we have things like Siri. We have speech recognition. We have these methods that are the best at doing things that are economically important that customers are using every day. There's a lot of value come from those systems, and I think there will be a lot of value, maybe more in the future for the vision systems. We'll have sentries and all kinds of automated vision systems that will be economically valuable. So I think that's what strikes me as the big difference.
Yeah, I'm wondering what you think of the relationship between human-level AI and consciousness. If one necessarily entails the other, if they're two separate problems, your thoughts?
My only thought about it is I don't know why people are always talking about consciousness, because I don't know what it is, and it's like it's a way for ordinary people to talk about human-level AI, I guess. Yeah, so I don't find that helpful at all. Yeah, it was funny, like you see ex machina, when they say, well, oh, you know what you've done? You've made a conscious computer. What you've done is what you've done. I don't know.
My question kind of dovetails on that. I see a lot of development in instrumental tasks and human-level approximations of instrumental individual tasks like finding cats or, just very specific things. What is the bridge between that and what you're describing as a strong AI, which may be incorrectly, I assume, is the ability to choose a set of actions out of a wide range and then execute that action?
So the short answer, which isn't a bad way to think about it, the short answer is reinforcement learning. Reinforcement learning is the technology of things that choose actions to achieve a goal, that sort of want things, as opposed to things like deep learning, which is just generalizing from a bunch of examples that people say what to do. Okay, reinforcement learning gives you autonomy. It gives you agenthood. This thing is making choices to get to achieve a goal, and it will try everything within its repertoire in order to achieve that goal. So that's the quick answer. The limitations of the current reinforcement learning I think of as being the thing that I was able to just briefly touch on at the end. They don't have good abstract models of the world. You know, they can form models of the world if it's a grid world. They can form models of the world if they're given good features. And there's a lot of theoretical ideas that are pertinent, but it hasn't really been demonstrated how they can come to an understanding of the world.
So you talk about the deep learning and talk about reinforcement learning. So how do you think about the deep reinforcement learning?
That's very much a part of this. The two systems from DeepMind could be reasonably characterized as deep reinforcement learning. The Atari game player, DQN means deep Q network, and Q is a reference to the value function that is learned by the reinforcement learning methods, as in Q learning. Okay, so you know, I'm obviously excited that it's not just plain deep learning, which is just memorizing training sets and generalizing from them, that there's some of my own field in those examples, the reinforcement aspects too. So I'm particularly excited about that, but I think generally that's seen as an important part of it. You know, all the excitement now, it's like, you know, I don't know, 3/4 deep learning and maybe it's 1/4 reinforcement learning. That's how it's being seen, I think.
You're about a third of the way through. You have the point of you phrased it sort of a rhetorical question about morality of lower intelligences enslaving higher intelligences. I think that's been addressed at length by Scott Adams in his Dilbert comic strip.
Oh, I gotta get a comic for that. Yeah, that would be good.
One thing you didn't say to reassure people who are fearful is that morality at some level will be derived from first principles by any great enough intelligence, and that any truly powerful intelligence will of necessity be good because it's done that. Did you not say that because you ran out of time, or because you fundamentally believe that morality is entirely orthogonal to capability?
I don't think it's entirely orthogonal, but I think it's separable. And I'm also very optimistic about these things, but my optimism comes not from thinking we'll all have the same goals. My optimism comes from, well, right now, we don't all have the same goals. You know, you could say, oh, we all love our children and we want to have food, but, you know, I love my children. You love your children, and the food I eat, you don't get to eat. So it's not true that we have the same goals. It's true that we have sort of symmetric goals, which often means there's competition. And yet, our world is full of full of cooperation. We do work with each other, and it's because it's rational. It's rational to work with people rather than taking stuff from people, because you take stuff from people, they get pissed off at you, and suddenly you're out in the cold or you're in jail. Okay, and so it's amazing fact. I'm seeing it as a fact that out of a society of many different goal-seeking agents with different goals, the right thing for them to do is to accommodate each other and cooperate and trade. And you know, there's comparative advantage things. Even if one agent is smarter at everything, so this is a standard economic thing. Even if like one guy is better at everything, he can do everything more efficiently. He still is beneficial for him to pay someone else to do something that other person can do worse than he could do, but he doesn't have to do it. He can do something that he's even better at. So there's lots of reasons why it can work out just by being rational. Okay, and you know, the real stupidities in the world, you know, come from wars and stuff like that. And wars are just not rational at all. You know, it's like you take over Europe, you don't win. But you inherit a devastated landscape and resistance. So super intelligent agents, I think, would be more far-seeing than us. They would say, oh yeah, we could have a war here because he insulted me or something. Or, you know, they could be more rational and find solutions that are better. That's why I'm optimistic.
So people like Marvin Minsky and Noam Chomsky have been skeptical of statistical models because they say, well, you know, you're solving engineering problems, but you're not working
on the scientific problem of intelligence. So what gives you confidence that more sophisticated statistical models will solve this scientific problem of intelligence?
So I'm tempted to just say, well, they're wrong, and they've been proven wrong. So I think it's okay to say that because they have been proven wrong enough times. We've had 60 years of AI, and we've tried it the different ways, and it keeps the statistical methods just win. They're sort of saying, well, they might win for a little while, but in the long run, they're not going to be winning. But the long run has happened. And so I think they're just expressing their biases. They didn't want those guys to win, but they have. And fairly, it was a fair fight. Okay.
What do you think about Toyota's humanoid robot, which take different instruments, go on stage, orderly manner, perform a concert, come off stage in orderly manner? Is that AI or not?
Toyota's robots?
Yes, I think it's Osmo. They created 15, 20 years ago.
Most of those, the ones that I've seen, they would be teleoperated. Okay?
Without control, remote control.
And I'm really impressed by them, actually, because they're demonstrating the dexterity of the hardware. So anyway, that's a strong impression I have about their robots, that they are showing great the capabilities of the robot hardware, how far it's come. But I don't think they're working on the algorithms, if that's really a focus. As far as I know for them. I don't really know much beyond that.
So during your talk, you talked about the central role of Moore's law in AI.
The central role of?
Moore's law.
Yes.
I wonder if you account for that, if you try to adjust, for instance, the progress of different machine learning problems, your error rate, you adjust that for Moore's law, what's the remaining part? Like, basically, what's the work of the AI researchers?
Yeah, I think if we could work that out, that would be cool. Yeah, does anyone know? Anyone just? I guess you can always, as more law comes along, you can take the old methods and keep running them.
Well, so a valid question is the improvement in performance growing slower than Moore's law? Do we need significantly more computation to get a slightly higher accuracy?
And that's clearly true.
From my perspective, it seems like that's true.
Yeah.
Which indicates that maybe intelligence or whatever you want to call it, learning, doesn't grow as well with Moore's law as we would like it to.
Yeah, it's hard to be clear about that. I mean, so for example, I think of it, the case I think about is like, again, the big chest searches. If you get a doubling, it doesn't mean you can look twice as deep, right? Because then the search tree gets really bushy. So you can search a certain amount deeper. And you can search basically twice the volume, okay? Okay, now what do we mean as being twice as smart? It might, if I was to guess, I would say it was more like twice the volume. If you can explore twice as many possibilities and find the best of them, then you're kind of like twice as smart. And even if you're not looking twice as deep, you're still considering twice as many possibilities. Now, if you're doing deep learning or some learning trying to get the last, half of a percentage point out of an error rate, obviously it can't keep going forever. You run into zero. But you need some other way of measuring how much it's searching and learning. Yeah, I don't know. Sorry, that's the best I can do. Maybe one more question or in the back.
So what do you think about the scalability problem of training people to use these techniques?
Scalability problem of training people to use these things. Well, I'm really into IA, intelligence augmentation, which means sort of merging with the computers and enhancing human intelligence by interacting with the computers. So I'm not thinking it'll be like training them. It'll be a deliberate goal to interface people to machines So like in the prosthetic, right? That's exactly that. You put a new arm on your body and you have to control it.
I was more thinking about the challenges of training students to be able to develop like AI techniques to
Training the students. So I know lots of people are working on that. Yeah, it's going to be difficult. I don't know what to think. I don't, because there's going to be vastly more knowledge. There's going to be these systems that are smarter. We do want to use them to help us. We don't want to. I don't think we want to enslave them. Of course, there might not be a problem, right? They may be happy slaves, or they may be happy to just work for us. I think that will happen in many, many, many cases, right? You will have the butler will be happy to serve us, or the car will be happy to drive us because of the way it's designed. But there will always be some that will not be happy to just do our bidding, either because something went wrong in their manufacturer, or maybe some AI researcher designed them to be independent. So we have to face this question. But for most cases, it might not. They are going to be on our side, and they will help us learn as fast as they and we are able to enable them to do that.
Up there? Maybe we'll stop. I'll ask you one question. So in the 20th century, we had a lot of negative results. We had things like Gödel's incompleteness theorem. We had this P versus NP issue and undecidability pop up. We had Heisenberg uncertainty principle. We know that we can't go faster than light.
Could there be a negative AI result?
Yeah.
I don't know. So most of those are math, and some of them were physics. Could there be a negative? Certainly there will be negative, like math results. And there are. It's commonplace to have, what do they call them? Lower bounds. It's either lower bounds or upper bounds.
Lower bounds.
Lower bounds on error, and for machine learning systems, and those are important, meaningful. They are meaningful negative results. And obviously, there's not going to be a negative result that we can't do as well as people do, because, well, at least I always think that way. I think, will machines ever think as well as people? Well, people are machines. They're biological machines. So I don't think that's not an issue there. Well, what else could we have for a negative result? There's going to be a limit on how much computation can be done in physical matter. Yeah.
Power limits.
Yeah, so someone asked about that. I thought of one more thing I wanted to mention. Yeah, there's the power limits. Yeah, so there are people who have thought about that carefully. There's a book, I think it's called The Intelligent Universe, which works on that. It does entirely with that question. Okay, so thank you very much, everybody, for all your questions.